Okay, a couple things, just before I forget it. So I told you I was gonna have makeup classes basically to make up for when I have flu and was out. So I'm gonna have one tomorrow. I know there's gonna be no one time that works for everyone. So I'm gonna give you three options. I'll be basically giving the same talk three times to make certain everyone has a chance. So the options are, I mean, and just pick one, just let me know, if there's a reason why. So Thursday. This is extra class. Okay, March. Let's be the 27th. Okay, one is gonna be at 10:45 to, what time did I have it? I think it's like 12:45 to noon. Kind of like that. That's one option. That's perfectly fine. I know there's a seminar or something at that time. I know at one point, Dean Gabby, I shouldn't call her Dean Gabby, Dean Gelston, okay. She said that she was giving permission for people to, whenever I was trying to come up with the time to make this class work. And I picked that time and it was during seminar. She actually gave permission for everyone to take it. If that's the option you want, I'll send her an email saying, please excuse so-and-so from the seminar, that they're coming to an official thing. So there's that option. The other one is gonna be from 12:10 to, that's about 2:20. Okay, to 3:10. And then the other one will be from 6 to 7 p.m. If you come to this one here, I'll try to get pizza and eat pizza, but I have to know if people are coming.
Why would you say that?
I don't know where to get pizza these days, but so let me know here which one. And then we'll go from there.
My first choice. I know, me too.
Okay, maybe there won't be pizza.
I go get that time.
Okay, so let me know just because basically I won't have had dinners myself, so I have to have food myself. So this is what I'm doing pizza. Okay. Okay, so there's that. You said you had questions?
Yes.
Yes.
So first of all, probably an easier question. When we look at the angel plot, you asked the question, how does the fragility of any liquid relate to the strong liquid in the
Yeah,
like
just talking,
the slope?
just that way I was trying to get to the fact that the fragility, I mean, good grief. The fragility for the strong liquid is as low as it goes. You're not gonna get below that.
Why can't we have lines that go above the y equals x?
Oh, there's no, I've never seen any, okay, I've never seen a plot of that.
Okay.
I mean, if you had data like that, then you could, but
Okay.
I've never seen a data like that.
I was wondering if that may be some theoretical calculation that says, hey, like.
Not that I'm aware of. I mean, the whole point of that, when I had it like this. Ooh, that's how long. Here, is that your strong looks like this, and all the fragile liquids I've ever seen are like that.
So nothing that goes.
No, there are some where you get these, and I couldn't tell you what systems they are. I think there's some that kind of go like this.
Yeah, I've seen.
But that's again, will then go to have the fragility of the strong.
Mhm.
So you can have ones like that I've heard about, though I couldn't begin to tell you what the system is.
Okay,
But for all the ones I've only seen the graph like this, I've never seen anything else.
okay.
So that's why, so you can have this, you can have this, but no matter what, this slope here, that's the smallest slope you can get, everything else will be larger.
All right. So then the second question is the viscosity at glass transition.
Yep.
So,
And that's all from Angel.
yeah. So he says, okay, our reasonable time scale is 100 seconds.
Mhm.
Sure, that's his assumption.
Mhm.
How do we get from those 100 seconds to the 10 to the 12 viscosity? Is it just from saying that?
I mean, experimental, I couldn't, okay, go ahead, I interrupted.
Would it just be derived from the fact that G at infinite frequency is like 10 to the 10th? Experimentally with the.
You mean the G,
In the Newton equation here?
you mean this here?
Yes.
This is actually, it has a fixed, okay, it claims to be a constant, I would have to look it up what it is, but it's, this has some who knows what value.
I mean, if we say that T is 100,
Mhm.
right, then A.
Oh, and then you're saying that this is, I've never heard that argument, but I mean, that seems plausible.
So, but I guess the general question, how do you get from the 100 seconds of the time scale to the viscosity of 10 to the 12?
The upshot is I don't know. Okay, because I've never done any of the experiments, and so I'm just entirely relying on him. My gut feeling would be is that when you go to the TG for glass, that let's say known TG, you get some viscosity for that, and then you do a number of them, you see they all have the same range, you just say, it's this.
Okay.
That'd be my naive thing, but I've never done that.
Okay, and what are your thoughts on the fact that, like, I think John is strongly believes that there's a glass transition region as opposed to like a particular time scale, or like a particular viscosity, because you were talking about fracturing of landscapes, and that is related, like but there's not one value where the glass transition occurs, right?
I think there's probably is a range.
Okay, yeah.
I think that's probably correct.
And would that, so that would correspond to just different mechanisms contributing to different relaxation times?
That would be a very reasonable explanation.
Okay, got it.
Okay. Okay, so what I'm gonna do today is talk about the disconnectivity graph. How you do those? We're gonna do something really simple. So when we do it, you're gonna say, well, I don't see why that's really useful. Again, with the point is gonna be that when you do actually a realistic system, these pretty little energy level diagrams that I've been drawing, you don't get. In fact, you can't really draw them. And so you really have to rely on these disconnectivity graphs to do things. And so that's part of the reason why we're doing this. And then I want to talk about ergodic, non-ergodic, and stuff like this. I want to kind of set this all up. What I handed out is, I told you that John and I were writing a book. Here's chapter 9 of it, which actually, let's just say there's more than one typo in this here. I'll just leave it at that. I think actually the text, I actually even might refer to it as being chapter 8 periodically. This has kind of moved around a lot in the book. There's been a lot of variations on this. Again, I can't say that I've dropped the ball on this book. As I said this morning, I've taken the ball and I put it in a deep hole and I put concrete over it, parked a truck over it, probably detonated a nuclear weapon over it as well. So that ball is, I don't know where that ball is anymore. Colin is now on when he came, I said, would you like to help? And he said, yes. And so I'm hoping with Colin, I'll be getting a kick in the butt, because frankly, I've looked at this so much, I can't take it anymore. I need intervention. So I'm hoping that there'll be intervention from Colin that will help me to finish this off. So we'll go from there. So I want to talk about disconnectivity graphs. So a useful way. Another useful way to view the lens. And I think there's an edge on that side, right? No, I'm good. Okay. View the landscape is by means of a disconnectivity graph.
You want to put lines? Here.
Okay, disconnectivity.
Oh, you guys misspoke already last time, but what?
Are you surprised by this? Disconnectivity. Again, my advisor spelled neutrino, not rhino. Okay, when your advisor spells it neutrino, not rhino, it's not going to go much. My advisor will pick up things from your advisor. Okay, so this is how this is going to go. So let's start off with something simple here. This is going to be your energy. And let's say I have something that looks like this. So I'm going to label the inherent structures with numbers. This would be 1 and 2. I'm going to actually use letters for the transition points. Okay, so I'll call this A. So this would be some V1. This would be VA. And that would be some V2. So you do the disconnectivity graph. You plot your energy this way. This is your energy. I'm going to put dots for each of these points here. So this dot here, this would be V1, that's point 1. It's 2. That energy V2. This point here. Okay. This is my A, and that's VA. Okay, what I'm going to do is I'm going to connect these points with lines. So there's a lot of options I can do here. If I wanted to, I could just have like a curved line like this. Okay, I could just have like straight lines like this. Perfectly fine. Traditionally, and this is just done to make it look aesthetically appealing. Normally, you have like a straight line coming up here, a straight line coming up here, then you bend them. And that's only for aesthetic reasons. It doesn't matter how you draw this. So in a case like this, the way this would traditionally be drawn is kind of straight, bend like this. Okay. But that'd be the disconnectivity graph for this. Now you could say, well, I don't really see the big advantage of this compared to this, and there isn't. Okay. The advantage will become when we have a really complicated system, and then in which case we can't draw the energy level diagram. And you really have to rely on the disconnectivity. Okay. So if I had this, or if I had this, or if I had this, these are all the same. Again, this just looks aesthetically a little more appealing, and this is why you basically do this. Okay. Now let's make this a little more fun. So let's say I had something like something like this. So this is 1, 2, A, B, 3, 4, and this is C. Okay, let's say that's our energy level, or energy landscape. So if I were to do the disconnectivity graph, well, what would you do? Well, I have my 1 here, and this would be V1. I have my 2 here. This would be V2. I'm going to stop putting these dotted lines going to, because it's just kind of a pain to do. And this would be my A. And so I would kind of do this region first, and then I look at this region here. So this part would be this. Actually, I just call this 2. Then I do the same thing then for this. So I have my 3, I have my 4, and then I have my point C here like this, and then I do have that. So this would be the disconnectivity graph for this little part, and this would be the disconnectivity graph. This would be the disconnectivity graph for that little part. But then I have to connect the two together. And so what I do, I'd have my point here B. So I'd have a straight line, bend, straight line, bend. And that would be my disconnectivity graph then for that setup there. And I do a more complicated one. So if you take the little handout on page 258, I give one like this, and I give you this is a slightly more complicated disconnectivity graph, but it's the same idea. And so what happens here is that when you actually have, let's say you have like, 20 particles or 64 particles, it doesn't really matter what, you're going to have inherent structures all over the place, transition points all over the place. You can't draw these diagrams, these energy landscapes like this. You really have to rely on this kind of thing for this. And the way John and I did that is, it turns out there's a very, very kind-hearted British physicist by the name of David Wales. And one of his students, I want to say it's Miller or something. I can't remember what it is. I want to say it's Steve Miller, but I think that's just a little rock guy. I can't remember entirely what his name is. He actually wrote a program which he gives for free. That basically, if you in the input for your for this code, if you give the inherent structures and the transition points, that his code will actually then automatically generate a disconnectivity graph for you. And so that we're actually using that. So, it's a very nice feature that he did. So, again, at this stage here, you could say, well, you know, I'm getting as much insight into this diagram from here. To here, I'm not really seeing where it's a big issue. But again, that's just because this is a idiotically simple system.
Yeah, that's one particle in one dimension.
Yeah, it's nothing. It's just like.
But
Okay.
if we were to have two particles, we could still have like multiple transition points and branch out.
Yeah, I mean, I guess these things get, John and I early on actually had we were, first learning about this, I can actually show, we were looking at some of the selenium systems. I can actually show you what they look like, the diagrams, and they're a lot more complicated than this. And we had to rely on, Miller's to build them. Okay. So we're gonna do some things like that. Now, before I go any further on this and start looking at the polymer entropy and stuff like this, what I want to do is I want to take a little bit of time here, talk about what it means to be ergodic and what it means to be non-ergodic, and because now we're to the point where we can actually understand some things here. Okay, so what do we have? So before we look at the entropy, for metabases. Okay. Let's discuss ergodicity and non-ergodicity. Now we can actually do it. So if I want to calculate the average value of some f, okay, what do we do?
It really depends how you want to calculate it.
This is like one of the early ones. Get a sum on I
At probably
F5 times UPI. Okay, that was fine. Now, what is this value? I'll give you a hint. That's a trick question.
What is the value?
Doing calculating an average value like this.
Always.
It's always a value. That's just the definition of what it means to be an average value. Now, question is, if we're in equilibrium here, what are the p sub i's? They don't have to be all the same. At a really, really high temperature, they're all going to become the same.
Okay.
But in general, if in equilibrium, these are going to be Boltzmann or Gibbs or something. They're going to be one of the equilibrium distributions we defined. So if the system is in equilibrium, the PIs are given by the Boltzmann distribution. Yeah, when you're doing the classical thing, then you integrate over all the positions of all the particles and stuff like that. We're gonna have to do that in the not so distant future. But this will be fine. The question is, what happens though if we're not in an equilibrium system? Let's ask what happens. If the system is not in equilibrium. Okay. But now we actually know what to do here. In a case like this, what could we do? Well, we would solve the mastery equations. Okay, in this case, in the case of okay, I'm just going to abbreviate this non-equilibrium. Okay, we can solve the master equations. For the PIs. So let's write down the master equations for one of these again. Now we've done it before, but we're gonna use so much of them. Tell me what this guy is. Sum on J, not equal to I.
Transition rate from
Okay,
J to I
keep going.
times the probability of being J. Minus
Minus.
the sum on J. Transition rate from I to J. That is the probability of being.
That makes sense? We have these. Now, how many of these equations are we gonna have?
No, however many inherent structures.
However many inherent structures. we're gonna have. So, we have, there are as many dpi dt equations as there are inherent structures.
Excellent.
Yep.
We start talking about time in the non-equilibrium structure, and here we don't mention time at all.
Hold that thought. Okay, it's gonna be this with this. Okay, so what do we end up with? We end up with first order coupled differential equations. So we have first order coupled differential equations that must be solved. Okay, in a case like that, that's so complicated, how do you have to do it? You have to do this numerically. So these must be solved numerically. And let's see if I'm not blurry. Cool, excellent. And as I joked this morning, I said, if you can actually take one of these systems and solve it analytically, I will make you be my student. Okay, I will not give you a choice. You're going to basically be my student. I'll give you a little desk by my office. And you have like a little name tag that says Roger's student. You know, I solve these analytically and stuff like this. You know, get a little picture of me going like this, thumbs up. You know, that's what you get if you can do this analytically. Okay. So, what would this give us? So if we solve this. So what would we do? We'd start maybe when we're at a very, very high temperature. At a high temperature, the PIs are going to be equilibriums. We basically put in our thermal history, and what can we do? We can then integrate these to give us PI at any given time. So what we can do, we can solve these. These equations can be solved. You would have to know all the aspects of the landscape. Okay. Can be solved for PI, and this is going to be a function of T. Okay. Well, hey, what happens if I take this equation, which is always true, and I put in my PI here, which I solve numerically now, which is a function of T? What does it mean about this F? It now depends on time. The F now depends on time. In a case like this F now, it's going to be a function of T as well. Okay. Now, when we do equilibrium, when we calculate equilibrium systems, what do we know about these F's? They're not a function of time. Yep.
Is it? Like, I realize that this can be any property, like.
Yep.
Any property. But do have eyes also depend on time sometimes?
You could, depending on what you're looking at, you can get these things really convoluted. Normally, it's gonna be like a position. So, okay, we're ultimately gonna connect this to the fusion. We don't know this yet. And so what we're gonna look in here, what's gonna be interesting is that we're gonna have a particle here at some time. Let's call it 0. And then we're gonna have another point here, we're gonna say R at a different time. And so that we're gonna have to worry about what that's gonna be. Is that what happens when they have this here, this particle here, and then sometime later on, that particle is gonna move over to here.
Okay.
And that's how we're gonna connect it to the fusion process. We're gonna start looking at things like this.
That's definitely could be.
Okay. And we're gonna look at something called a correlation function. And the correlation function is a quantity we have here, will be explicit functions of time. We're not there. Again, I've completely restructured how I've done this class. And so I don't, how far we get, I honestly have no. Again, I've entirely restricted it.
We're gonna stop in the middle and improve.
Yes, just last, put on, this is the most important thing to know. Have a good summer. Enjoy your break. The joke on that. Okay, so Colin asked me to be one of the moderator for one of the sessions at GOMD. I said, sure, I'll do it. It's in Vancouver. And whenever I've gone to GOMD before, these meetings have always been around the end of May. Yes, and I just naively thought that this would be the same case this time. And then, somehow I was looking through some stuff and I looked at the date and, oh, like May 4th, May 5th. Isn't that during finals week? And so I really don't quite know what's going to go on now. So, I mean, you joke about ending the class in the middle of a proof. That very well may be happening because I think my whole finals week is now messed up. And I have absolutely no clue what I'm going to be doing yet, but don't tell anyone because I don't want to create panic. So, okay, we'll go from there. What are we talking about? Oh, this. Okay, it's not a function of time. Okay, so one of the hallmarks. So there.
Ergo.
Ergo. We haven't had ergo. Ergo.
There it is.
So this well. So ergo. What are the hallmarks? Of non-equilibrium systems. Is that these values here depend on time. I know this is F dependent. Okay. Now, if I wait long enough, let's say T is really, really large, what will this thing reduce to? It's going to reduce to equilibrium. So no. If T is very large, in other words, i.e. T goes off to infinity, these values here will also go into this F and these equilibrium systems. Okay.
Don't you think it's a little more representative to put the function of T outside the
I'm sorry, don't like that.
It's like now it looks like F is a function of time and you're averaging that. But F might
Yeah,
not be a function of time.
I agree, but it's almost, I've never,
I think it's a good way to do it.
that just looks weird. Okay, but it's, I mean, it's, the point is well taken, it's just, I don't know how to write it well, because that's just. Okay, and I've never seen it. Sure. Okay. So what I want to do now is talk a little bit about two types of averages. So now I'll mention the same thing that I've mentioned this morning. So I'm going to go to a discussion by Rife. I think it's spelled like that. Okay. He has a classic statistical mechanics book. I thought it was a Dover book, but it turns out it's not a Dover book, but I gave a little talk about Dover. Are you familiar with Dover? No,
The
this,
publication.
this is the guy's, this is his last name. There's actually something called Dover, and it's a public, they publish books, and it's something actually that you might want to be familiar with. Because what they do, they'll take older titles, and some of them are not that old, it can be like late nineties, early 2000s, so sometimes not that old. And what they do, they produce a relatively cheap, high-quality paperback version of it. So if you wanted to build up a physics library or chemistry library or whatever, actually, Dover is one of the first places you might want to. So you can actually get some really, really high quality books that are well bound for something to read. So if you need to build up a physics library, good place to look. Okay. I thought this was actually a Dover book. I checked my book, and maybe it is. I checked my book. My book is not a Dover book. It's some weird publisher that I've never heard. But he has a classic text. So what I'm going to do is I have it printed out. I won't give it to you now because I didn't give it to the morning section. I want to keep the two the same. So what I'm going to do is I'm going to give you his little discussion of what he talks about ergodicity and non-ergodicity, because I think it's actually one of the better ones I've talked about. So I want to talk about Rife's. So let's look at. Yeah, Rife's discussion. Of ergodicity. So this is how we're going to do it. So Rife makes a comment that there's really two types of averages we want to look at. We want to look at it, we can look at time averages of quantities and also ensemble averages. Now this isn't Rife coming up with this. This is just Rife discussing what has been known for a long time. So there are two common types of averages. Time averages. I guess I should use it for time averages. Okay. And ensemble averages. Okay. And with the ensemble average, there's a way that we don't normally think about ensemble averages, but it's a good point. That's this. So normally, when you think this is thick, think about ensemble averages. Right. And that's completely correct. But there's another way to look at these. And it's this, and this is what Rick does. And he has a nice little picture of how it's done. So what I can think of is I can think about having a large number of identically prepared systems. So imagine a large number of identically prepared systems. I'll just say identical systems. So here's my first system. Here's my second system. Third system. Here's my kth system. I go all the way down to my nth system. Now, what I do is at the same time for each of these systems, I measure whatever my F is. So at time, this is, so at time t, we measure F for
Average.
whatever it's gonna be, it'd be like the average F for just, I'm gonna say energy, what else, yeah. You could,
I'm just saying.
it's gonna be whatever, it's gonna be, it's not necessarily the average, it's because we're gonna do something to get the average. It's gonna be, let's say, the energy. So at some time t, let's say it's the energy, I'm gonna take the energy of the whole system at that time.
But that's still like, that's U equaling average.
No, it's gonna be whatever the actual energy is, so now imagine if I had like kinetic and potential energy, if I took a snapshot at that point. And I could get I could get the velocity of each of the particles, I know the potential energy, I could calculate the actual energy at that time.
Oh, so it's in 1 microstate?
Exactly, okay. So, measure F for MT, we measure F for each system. So I measure this one, I get F1, this one here, I get F2, this one here, I get F3, this one here, FK, this one here, F. The expectation value, or ensemble average, is going to be the average of these. This guy right here is really going to be 1 to n, someone on it from 1 to n of whatever we set for.
Sure, because now we cover all the microstates.
Correct.
here, right?
Okay, and this is going to be based, but I'm doing it at one time.
Mhm.
This is all at one time. This is all measured at time. But I could also, what I could do is I could look at a time average. So I could take one of these systems here, he takes the Cape. And so what I could do is I could take the Cape system here, and I can measure this over a period of time. I could take the time average of this. So, and the time average. We take one of the systems here. Let's say the Cape one. And time average up. Over some time. F T. We're gonna do this. So I'm just looking at this one here. So I have basically, I'm taking a little film of it. I'm gonna set it sometime little t, go to time little t plus t. I'm gonna calculate all the energies during that time here and take the time average of it. So what we have is the following.
So equilibrium those.
Well, we're gonna do a transfer names. So what I'm gonna do is I'm gonna take the time average of this guy here. This is gonna be basically from sometime t plus dt of my Cape system there. Here. This is the function of t dt. One over t. Now, the system is ergodic. What do you think is going to happen? This value here is going to equal, ensemble average, and that's a formal definition of ergodicity. So when a system is ergodic, time average equals ensemble average. That's it. So let's say I'm in equilibrium. What's going to happen in equilibrium?
There's no, so all the probabilities, all the inherent structures can be explored. So we're gonna get all the probabilities if we wait for long.
Mhm.
So that means that it would be the same as looking at all the probabilities, just in different structures.
These will always be the same in equilibrium. So in equilibrium, this will be the case.
So you break the ergodicity if there's like even at least one energy barrier in the energy landscape that you cannot overcome
Well,
in the system.
not necessarily. not necessarily, depends a lot if I wait long enough,
Yeah,
okay? In other words, if this capital T is long enough, okay, what's gonna happen? Well, then I'm gonna eventually go to near galaxies. I'm gonna have an equilibrium system. Okay.
yeah, so the rates could never be zero, is that what you're saying, like either.
Well, what I can remember, I'm looking at the time here like this.
Yeah,
So maybe here it's all screwed up and these are not the same at all. But if I wait a long enough time, let's say over here, all the things have happened and this is gonna be equilibrium. Okay.
but like energy landscape wise, so that would just mean that there's no way to get like a zero transition rate.
Yeah, everything's gonna be, there's another way of looking at this thing. Okay. So this is what it's gonna mean to be ergodic. So non-ergodic is gonna be, these are not equal. So a non-ergodic system, so in a non-ergodic system. Okay. These two averages are not equal. Now, okay, I'm gonna tell you the traditional way that people look at ergodicity. And I'll tell you a story which is true, and I don't know how to reconcile this with anything, but it's a true story. So the traditional way, it's the way I've always understood ergodicity. So the traditional view of ergodicity is that the system, okay, has sampled all available configurations. And that's my understanding of ergodicity. Now, here's where it falls apart, and I don't know how to reconcile this.
It's scary that you're saying it's falling apart.
Well, it's just, I'm gonna tell you this situation, and I'm gonna say I don't know what to do with it. So when John Pravat and I were working on the interview for Glass, there was a question on something. And so Pravat insisted that we had to go see Joel Leibowitz, who I think is at Rutgers, and I checked and he's at Rutgers. I don't know if he's still alive or not. He was ancient when I saw him. To talk about some aspects of ergodicity. And just, this is an aside I told this morning. So it turned out, and he's the only one I've met like this. He was actually, a survivor of a concentration camp when he was a little boy. So when he was a little boy, basically his whole family were basically being massacred in brutal ways. You know, he actually even had the tattoo, you know, on his arm that they were all the Jews were living with them. And he was a really kind and decent man. And I guess when everyone else was asking about this, all I could think about is, you know, if my childhood was being spent in a concentration camp, I saw my entire family massacred. You know, because he was probably in his 80s when I met him. You know, would I be this kind, decent man in my 80s? Or would I be this bitter old man who just hated everything and just, you know, was messed up in my life? And he was not. And just, I guess I could not really get past that when I met him again. Okay, that's side. Okay, but here's where it comes in. He said he was with I think one of his postdocs. And they did a calculation of, I don't know what, I can begin to tell you, remember what the system is. But they actually explored this idea. And he said that there were some systems that were ergodic, that large fractions of that landscape were barely being visited. He said if you looked at the time scale to visit some of these sections, it'd be like millions or billions of years. And so this idea that the space is being sampled, he said was just utter nonsense. Now he was really, really smart. Might still be smart. I don't know, because I don't know if he's alive or dead now. I think he probably, this would have been like 2008. And so I think he probably is not alive. Again, he was ancient when I saw him. But when somebody really, really smart says something like that to me, I'm not going to dismiss it. And so I don't know what to make of that statement. I'm going to stick with this because this is what I'm familiar with. But again, just so you know, you might come across somebody who says, well, you know, maybe not. Okay, I'm going to stick with this. Just throw me in. Okay, so we have that. So that's what it's going to mean to be non-ergodic. So now what we want to do is I want to actually look at basically how we can look at the energy of a landscape as as we cool the system and what's going to happen with the system that basically we're losing actually people that are in the system. How do we calculate the entropy? So let's ask how. So as a landscape is cool, how do we describe? How do we calculate the entropy?
Yeah,
Yep.
like, it's bothers me.
Oh, it did me too. I have no reference.
So that would probably happen, most likely, is dependent on how they measure the ensemble average. And it's fine, like theoretically, n has to go up to number of possible energy states, right? To measure the ensemble
Yep.
average, right? You have to get that.
See, I have no idea how they even approach that.
So
I don't have no idea how the calculation was done.
But usually how they measure ergodicity is they make one sample and they take pieces of that sample and look at like different pieces, different sites of that
Mhm.
sample. And they say, okay, this is our ensemble average of one big sample, but we look at different parts of it. So there's probably what was happening. I don't think this statement is wrong. I think probably what was happening is that there's systems in which there are some like probability, like there are some regions of the energy landscape that just do not get explored by the whole sample.
That's very possible. But again, I'm not gonna he was really smart and he knows this really, really well. And I'm not gonna dismiss what he's saying. And I'm saying I don't know how the calculation was done, but I'm not gonna dismiss this statement.
That's a very interesting.
Okay. So, and he was quite adamant about it. He went, these parks hadn't even been visited for like millions of years. And so. Sure. Okay, Joel, you know more than I do. Okay, how do we calculate the entropy as the landscape
You started that.
fractures? In a mental sense. And what we're gonna do is one of the first approaches is by, we'll start this tomorrow, is by Palmer. He did this, I believe, in the 80s. This is actually a very good paper. At some point he had a stroke. He was a physics professor at Duke. Whether he's still alive or not, I honestly don't know. I know after he had the stroke, I don't think he do physics anymore. But it's a brilliant paper, and we're gonna start there. Okay. So I'll set this up next time. It's actually kind of it's a beautiful argument. It's very straightforward. When you look at it, go, of course. And then I want to show you then what John provided to extend the argument. I think we made it general. I would actually argue that we have a very general technique for any type of system like this, and I would say we're correct. And what it's going to mean is that if we're correct on this, that at t equals 0, the entropy of the glass is 0. And there's actually no way out of it. And then I will talk about the Gaussian paradox and Gaussian temperature and stuff like that. So I think it's utter nonsense. Okay. Have a good day.
I think Dr. Philbin talked about Leibowitz one time.